No, okay. So last time we learned about concept of basic probability and its distribution. Before reviewing it, let's do some issues when any statement by government is announced. So there can be some ethical problems. Ethical problems in probability. What are these problems? These are the issues when any statement made by some company to announce some kind of a probability that can be misinterpreted. For example, a lottery company says, I'm just giving you the book example, the lottery company is saying that, okay, we won't stop until we make you millionaire. So it means like you keep playing and you don't know what are the six best numbers which can make you win the lottery. But in that case, the probability is being misinterpreted. So if a person, because persons they don't own, like individuals are normal human, they don't know about the probability, how to calculate the winning probability of numbers. So, and on the other side, like the advertising company, they are advertising it by that, like they won't stop until they make you millionaire. It means they are asking you to invest it without telling you what is the probability of winning. So sometimes it can be used by the advertisement agencies or by the government, especially by governments can make up the plan that there is a chances that there can be a new infrastructure built in certain area, and because of that the house prices gets higher and people has invested in those areas and this kind of probability. So it can be used for and against of making any decision. Then there was a concept of Bayes theorem. Uh, what is the Bayes theorem? It's a summation. It's just like um, a summation of conditional. You know about conditional probabilities. So it is an extension of conditional probability. It uses previously calculated probability by using a Bayesian analysis, right? It is also known as a revised probability. In this case, like we have like a conditional probability that A given B. Now, based on this information, we calculate the outcome, we calculate the likelihood of event A, whereas B is given. Or in other case, B is in conditional probability. When we extend the conditional probability and use further historical calculated probabilities, right, then it's known as we can do it with a Bayesian analysis. So there is a whole case study. You should go through that case study from the book, and if you face any problem you can ask me. Otherwise we will we will give some or allot some time to understand Bayesian analysis, that what exactly Bayesian analysis means in next week. So let's go back to the probability distribution of a discrete, yeah, that's discrete variable. Now, where here we will cover some key concepts. That is probability distribution from a discrete variable, from binomial. So remember, in discrete, under discrete probability distribution, there can be, first of all, we already learned and we will learn a bit more. Let's take an example on the board of discrete variable. But first we will see that how other types of discrete probability distribution. So we will cover Bernoulli distribution, then binomial distribution, then Poisson distribution, then hypergeometric or geometric distribution. All these are the extraction from the discrete probability distribution. And discrete probability distribution you already know. So let me take you to the whiteboard where we can see how we can go, or we can take an example. All right, so you can see let's okay, just for fun I wrote it. And let's say that what is discrete distribution, right? So what we're gonna learn today, that let me try to cover the topic today. um, we will learn Bernoulli, binomial, Poisson, Poisson, covariance of probability distribution and its application, and hypergeometric distributions. So in this section, we're gonna cover all these. So remember, all these can be extracted from the discrete probability distribution. So that's why it's really important to understand the discrete probability distribution. Right? You can see it clearly. So we have a probability distribution for a discrete variable. You know what is discrete and what is continuous, right? I don't need to explain further, because discrete it can be given as an example of number of pizzas, number of students in the class, number of coffee, a cup of coffees in the cafe shop sold. All these are the examples of discrete variables where you can have a whole number like integer. So when you are dealing with the integer value, then we call it discrete probability. Integer value means 1, 2, 3, 4. So we can say a probability distribution for a discrete variable is a mutually exclusive list of all possible numerical outcomes along with its probabilities. Probability of occurrence of every outcome. Can I say that? For sure, I can say that. So that's about the discrete probability distribution. For example, I have a distribution of you, like in my class. Now there are 32 students who joined the class, and 24 are not in the class right now. What I see here in my this software, right? So I can see the list of 32 students and 24 students who didn't join. What can I say? I can say that what is the probability? What are the likelihood? What are the chances of the students who can join the class during the class, right? So let's say there are 24 students, and I have to make a table. So I'm interested in like not the students who are already in the class, but I'm interested in that students who joined during the class. So that's my X. You can see, you can read it properly, or can you? Or can't you? You can read this, right? Maybe I can use different students who joined during the class. Not before the class, not at the end of the class. You guys can hear me, right? And you can see it properly. Okay. Oh, okay, you got, okay. Okay, that's good. I just saw the replies. I was asking you on the WeChat and group. So let's say student who joined the class during the class, they can be maybe none of 24, because right now 24 students didn't join the class at the moment. None of them will join the class. I mean, all of them will be absent. Maybe one, two, and so on, three, and so on, 24. So let's just consider it like until three students. So I have like three students. Otherwise, it will be 24, and then I will be having each probability of each student x equal to x against it. And let's say it's like because the sum should be always equal to 1, right? So let's say I have this 0.5% chances. I'm just giving you a random variable, and 0.25 and 0.15, um, 40, and then 0.10. So the probability is 1. So how can I draw? I can also draw it with 0, 1, 2, 3, and these are the probability of 0.5, 0.4, 0.3, 0.2, 0.1. So when the student nobody if nobody will join the class during the class, that's probability is pretty much high, right? And similarly, 0.25 is one student will join, and very few is this one. So and this one. So this is how I draw the graph, and this is how I give a contingency table. So what will be the expected value of the discrete? Expected value we already learned in last lesson in detail that it's like a mean. It is a mean, right? So how to calculate mean, you already know that. Mean here is mu, which is given as expected value of x. So which is sum of x I p of x equal to xi. This is general formula from I equal to 1 to n. So what do I need here? I need a column of x and px. And then I'm going to take the scale. So the student who joined n times multiplied by their probability. Right? So 0, 0.25, it's going to be 0.30, it's going to be 0.30. So what is the mean? 336, 6 and 2 and 5, 85, 0.85. Right? So is it possible to having a mean 0.85? Just an example. Is it possible? Tell me. Is it possible to get this average? What do you think? Is it possible to get this 0.85? So what does it mean? It means that on average, there are 0.85 students who will join the class during the class. So does it give you any sense? Because to me, it doesn't give any sense. For me, it's simply not possible because I can't divide the students into 0.85. So maybe like a student, if I consider this one, it means that on average, like students get into the class without a head or something like that. So then it's not possible in terms of discrete probability distribution, right? But in continuous, that's possible. In continuous example, that's possible. So in discrete, we will just maybe round up of these things, and that includes the error, the standard error for between the actual mean, because this is the estimated mean. We get 0.85. This one, 0.85, and we can say it like one student can come in. So that's the average. And hence we have to go further for standard error or standard deviation of a discrete variable. How to get that? So we know, just like that mu is this one, expected value of x. So what is the standard error, standard deviation or variance? So what is the variance of formula is that sigma square. We know x minus expected value of x, right? So if you solve it, you can get it sum of x minus expected value of x square into t probability of x equal to x. So first you have to calculate x minus expected value of x square. And look, this is expected value of x. So x here is 0.5. So you can calculate 5 minus 0.85 minus 0.35 square, and then here 0.25, so 0.6 square minus 0.6 square and minus 0.7 square and minus 0.75 square. And then you can multiply this with the probability. So the answer of this times 0.5, this times 0.25, this time 0.15, this time 0.1, and you can calculate. x minus expected value of x square into p of x equal to x. You can get it, and the summation you will get from here. And that will be our variance. Now, after calculating, it should also give you some values in with decimals. Yeah, so taking a root of the variance, it will give you the standard error. So do you understand this example? So sigma equal to standard deviation is going to be the root of sum of x minus x, root of x equal to x. So that's how you calculate the mean, variance, and standard deviation of a discrete probability distribution. As we discussed, that there are two kinds of distribution, that is discrete and continuous, and that's how we know in details how can we create the probability distribution through random variable, right? So if random variable is discrete, similarly we also discussed how to create distribution functions, that is non-decreasing function, right? We already talked about this in details in last lesson. There can be further specific discrete probability distribution, as I told you, and the basic one is Bernoulli distribution, and we're gonna start today with the Bernoulli distribution. What exactly is Bernoulli distribution? Let's have a look. So this you understood, the discrete probability distribution, right? How we calculate mean, variance, and standard error or standard deviation. Is it clear? Do you have any question? Uh, do you have any question? So, if you don't have any question, we go forward and I take you back from the screen, from the whiteboard to the screen. Now, look, you now you are able to calculate expected mean of any discrete distribution, expected variance, and expected standard deviation. Let's talk about a Bernoulli distribution. What is exactly Bernoulli distribution means? How do we construct it, and in what kind of situation we have to use it? It's it's also known as Bernoulli process. Um, so you can also use it as a oops, Bernoulli. And what exactly Bernoulli process is that when we divide the outcome into only two parts. So whatever we are interested in, it's that part. So it's a process in such a way where you can divide the outcome of event into two parts. Only two parts. Now, their probability can be different. It's not necessary that if their probability should be 1 by 2 and 1 by 2. Their probability can be 0.75 and 0.25, 3 by 4 and 1 by 4. That's also Bernoulli distribution. So we are not talking about the probability here. We're just talking about that it's a process where we can divide the outcome of an event into two parts. That's it. Means yes or no, success or failure, success or no success, do and don't do, head or tail. So whenever we have in an experiment, we have an outcome in only two possible shapes, in two possible ways, that we call it Bernoulli. And when later on we will see the other types which we extract from through the Bernoulli distribution, that's binomial distribution and others, is also based on these two outcomes. So again, likelihood is different things. The likelihood of yes and no can be different. It's not necessary that it's 0.5. In case of head and tail, it's exactly half and half, like 0.5% likelihood, 50% likelihood is of head, and that head will come in a fair coin, and 50% means tail will come. Now, you tell me that rolling a dice, does it come under Bernoulli distribution or not? Yes or no? Rolling a dice. Rolling a die. Does it come under Bernoulli distribution or no? Yes or no? Now we roll a die. So no reply so far. Okay, anyway, what are the outcomes? Does it rolling a die have like two outcomes? No, it can have six outcomes, right? 1, 2, 3, 4, 5, 6. In a very early example in this session, we have talked about this. So mostly it's if I draw a diagram, so let's say this is a time of experiment, and I have done different experiments, right? So let's say this empty part is not 0, means there's like no outcome. So it's also no outcome, it's also no outcome, and I found something here. So that says yes outcome or success outcome. Then I again found yes. So I have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's say that I repeated the I flipped the coin 10 times, and from 10 times I got this kind of a distribution, right? So I got yes and I got yes again. 1, 2, 3, 4, 5, 6, 7, 8, 9. And again here also yes. Right? So in this diagram, each point of each section showing any outcome, like first one is having a circle, right, which means success. So if there is a success, if there is no, if there is success, it's a circle, and if there is no success, it's an empty one. So circle or not or 0 indicates the success. So now if we consider that head and tail example of flipping a coin, so if there is no head, then simply it's an empty one, right? And if there is a tail, then it's a circle. If there is a head, then it's a circle. So we divide the whole numbers of experiment into small portions, and every portion is indicating that whether is a weaker event happens or not, whether the event happens or not, whether it's going to be head or not. All right, so you understand this diagram? This is a Bernoulli distribution. So I can say that it's a process using an independent. And yeah, one more thing, um, that in this example, each head is independent of another head. So we don't consider. So it can be possible that all this becomes head, and it's possible that all becomes tails and all becomes empty. So every head is independent. Every outcome is independent to another, right? So there's also one key feature of Bernoulli distribution. So a sequence. Now here we call it the probability. A sequence of independent Bernoulli trials that's random occurrence with two possible outcomes, only two possible outcomes. So at each trial, let's say we give a success a probability p and failure probability 1 minus p, because we know that total number of probability is 1. All right, so because there are only two outcomes, so it means whatever x is, the probability of x is, the other part of the outcome is must be 1 minus p. So sometimes we also consider p and q. Sum of p plus q is 1, whereas q, I'm just giving an example by showing in a book, you can also call it pi, right? You can label it anyhow, but I just consider it p and q because it's easy to understand. So whereas q is 1 minus p, all right? And p is 1 minus q, right? I will tell you why do I write in this way. Because when we go to the binomial, we will see that we need P and Q. But this is a possibility. So Q is a probability of a failure and P is a probability of a success, whereas Q is 1 minus P and P is 1 minus Q. So when we have only two outcomes, 1 and 0, that's known as a Bernoulli process. Yeah. So let's well, sequence. These are the examples. Sequence of lottery wins and loss. So either you can win or you can lose. So what is the sequence like? First you win with a probability P, then you win with a probability P again. So that's why I'm telling you that this is independent. So one outcome is totally independent of others. So one outcomes in every time the probability will be P and Q. So as I draw the diagram in this way before, so here if we have a success, so its probability is P, and here again if we have a success, its probability is P. So every time this event, this outcome, either it's success or failure, it's an empty box or it's a circle box, it must be having independent probability of P and from P and Q, whereas Q is 1 minus P. So you can also refer it as a Q. All right, so this one, I'm just mentioning it with a different letter, alphabets. So that's how we define the Bernoulli process. So in case of lottery win and loss, so every time we have a chance of either winning or losing, right? So there is a possibility, there is a likelihood of P and Q probability. So every time we just mention it. Let's say this time we win, this time we win, this time we lose. So this time we again win, this time we again win, this time we again win. So possible, that's possible. That's because every time there is different, there is a independent probability. So let's take arrival of each second to a bank. Now you can also mention it as a time. Right, so let's say one section is time, and you say in 5 seconds, who comes to the bank first, right? So in the first 5 seconds, does someone comes? Then in next 5 seconds, does someone comes or not? Then in next 5 times, does it come or not? So we can distribute it according to time as well, right? So at each time slot to server. That's what we have in Bernoulli. Now, in two outcomes, we have two probabilities, as I already told you, P and Q. So again, if we can divide any experiment into two outcomes, such a process is known as a Bernoulli process. We use it as a memoryless and discrete time. As I told you the example of time. So how do we use it? This Bernoulli process used as memoryless and time discrete time. What does memoryless means? Yeah. Now, memoryless means that if I get ahead in a second flip, then it has no relation with the first trial or flip or third or fourth. So every time, as I told you, the probability, it should be having the same P and Q in each outcome. So it is totally independent. So every time head is independent, whereas discrete time means that in first time interval the event occurs, or then in another time. So that's how I already defined to you. So this Bernoulli process actually helps us further to generate discrete random numbers. These can be included. These can include binomial, geometric, negative binomial, hypergeometric, and these numbers. You must have known that binomial means the same, the Bernoulli, but what's the difference between Bernoulli and binomial that we're gonna talk about in after the break, after the 5 minutes break, and then what is geometric, what is negative binomial, what is hypergeometric. So today we will cover everything about binomial and Bernoulli, and then we will just solve some examples as well. But just remember that binomial, all these are the forms of Bernoulli distribution, means we have only two outcomes, that is yes and no situation. But when do we say that this is now binomial or Bernoulli? That's I'm gonna describe you after the break. So if you have any question so far, you can ask me. We'll try to answer that.